Excelentíssima família do engenheiro Manuel Rocha, Excelentíssimo Sr. Presidente da Sociedade Portuguesa de Geotecnia, Professor Paulo de Venda Oliveira, Excelentíssima Sra. Presidente da Associação de Geotécnicos Antigos Alunos da Universidade Nova de Lisboa, Professora Ana Paula Silva, Excelentíssimo Sr. Dr. Ricardo Oliveira, Senhoras e Senhores, colegas e convidados. É com grande satisfação que vos dou as boas-vindas a esta sessão da Lição Manuel Rocha, um momento de homenagem, mas também de inspiração. Um momento em que olhamos para o passado com respeito, para o presente com responsabilidade e para o futuro com confiança, tal como o faria o engenheiro Manuel Rocha, a quem hoje prestamos tributo. Figura ímpar da engenharia portuguesa, Manuel Rocha foi diretor do Laboratório Nacional de Engenharia Civil entre 1946 e 1970 e é, ainda hoje, uma das suas referências maiores. Sob a sua liderança, o LNEC afirmou-se como instituição moderna, científica e inovadora, comprometida com o desenvolvimento do país e com a aplicação do conhecimento ao serviço do bem comum. Foi um homem de ciência, rigoroso e exigente, pioneiro em áreas fundamentais como a mecânica das rochas e as barragens, deixando contributos que projetaram o nome de Portugal na comunidade científica internacional. Mas também foi um homem de pensamento, que compreendia a engenharia como uma disciplina humanista, profundamente ligada à ética, à educação e à responsabilidade social. A sua dimensão pedagógica foi notável. Manuel Rocha acreditava que formar engenheiros era mais do que transmitir técnica, era educar para o raciocínio, para o espírito crítico, para o serviço público. Promoveu no LNEC uma cultura de aprendizagem contínua, de debate de curiosidade científica que permanece viva nas novas gerações de investigadores e técnicos que ali trabalham. Foi também um homem de visão política, no sentido mais nobre do termo, um cidadão consciente de que o progresso científico é uma escolha coletiva e estratégica. Defendia que a ciência e a engenharia são instrumentos de soberania, pilares de um país moderno, seguro e capaz de decidir o seu próprio futuro. A sua intervenção pública foi sempre pautada por uma ideia de missão, pôr o conhecimento ao serviço do desenvolvimento nacional, da segurança das infraestruturas e do bem-estar das populações. A Lição Manuel Rocha é, por isso, mais do que uma evocação do passado. É uma oportunidade de refletir sobre o papel do conhecimento e da investigação através das personalidades ímpares que têm e continuam a ser convidadas a proferi-la. É com particular satisfação que assinalamos que esta é a 42ª Lição Manuel Rocha, a cargo da professora Jean Hutchinson, do Canadá, que hoje nos traz o tema Considering Engineering and Geology in Optimizing Rock Slope Stability Risk Assessment, um contributo exemplar para o diálogo entre a investigação da excelência e a prática da engenharia ao serviço da segurança e da sociedade. Permitam-me sublinhar o significado especial desta sessão para o LNEC, por ser a primeira em que o laboratório se associa a convite da Sociedade Portuguesa de Geotecnia e da Associação de Geotécnicos Antigos Alunos da Universidade Nova de Lisboa, o que muito nos honra e que muito agradecemos. Hoje, inspirados pelo exemplo de Manuel Rocha, reafirmamos o compromisso que nos guia há mais de 7 décadas, investigar com rigor, inovar com responsabilidade e servir com ética. Que esta lição nos recorde o valor do conhecimento, que o conhecimento está sempre na sua capacidade de melhorar a vida das pessoas e de fortalecer o país. E que o espírito de Manuel Rocha, feito de exigência, curiosidade e sentido do dever, continue a iluminar o caminho da engenharia geotécnica portuguesa. Muito obrigada.
Muito boa tarde a todos. Cumprimento os membros da mesa, nomeadamente os representantes das duas instituições que, de forma continuada, desde 1984, patrocinam as Lições Manuel Rocha realizadas neste auditório, gentilmente cedido anualmente pela Fundação Calouste Gulbenkian, a quem muito agradecemos, bem como à professora Laura Caldeira, quem muito estimamos e que acaba de fazer a sua introdução. De todas as 42 lições Manuel Rocha, apenas a 30ª foi realizada no grande auditório do Laboratório Nacional de Engenharia Civil, integrada no programa do centenário do nascimento de Manuel Rocha, sendo que 21 lições foram proferidas por portugueses e 21 por colegas estrangeiros. Uma saudação especial para os filhos, nora e genro, Manuel Rocha, a quem me ligam profundos laços de amizade. Os filhos, porque os conheci crianças, sempre acompanhando a vida pessoal e profissional de seu pai, a nora, e o genro, que conheci mais tarde em São Paulo, no Brasil, e porque tem também uma profunda estima. Final greetings to Jean's family present here. Daughter and husband, who is a distinct colleague, also specialist in rock mechanics and geological engineering, and professor in the same university. After the death of Manuel Rocha in 1981, several institutions in the world, including LNEC, organized events to honor his memory. However, only the ISRM, International Society for Rock Mechanics, establishing in 1982 an annual award called the Rocha Medal for an outstanding doctoral thesis, and the Association of Geotechnics former students of UNL and the SPG, organizing the Manuel Rocha Lecture annually since 1984, are the only activities these two regularly offered to the international geotechnical community in the world. Respecting the initial purpose of honoring Manuel Rocha, as it was expected to be, it happens that we have with us today one recipient of Rocha Medal, who is exactly the husband of our Professor Jean Hutchinson. He received the Rocha Medal, is sit there. He received the Rocha Medal in 2002. And I hope, because I asked him to be here among us, that the first recipient of Rocha Medal was our colleague Pinto da Cunha, who received this medal in 2002. 1982, I'm sorry. Is not, Pinto da Cunha is not present? It's a pity he didn't come. Another Portuguese colleague, Ricardo Rezende, received in 2014 a runner-up certificate, which is given sometimes with the medal. The translation in Portuguese is menção honrosa. Dear Jean, we were very pleased with your prompt acceptance of the invitation to deliver the 42nd Manuel Rocha Memorial Lecture and to write its content for publication in the next issue of the international journal Soils and Rocks. It was with great pleasure that I have agreed to make your presentation to the audience, moreover because both our scientific and technical activities and interests cover similar areas within engineering, geology, and rock mechanics. Jean Hutchinson is Professor Emerita of Geological Engineering at Queen's University, Kingston, in Ontario, after a retirement at the end of last year from the university. And she is Vice President of Innovative Geomechanics Incorporated. This company, I was not sure, but now I am sure, belongs to the couple. The couple is owner of this company. Jean Hutchinson graduated in geological engineering at the University of Toronto, his bachelor's in sciences in '84, in civil engineering at the University of Alberta, Master of Science in 1988, and got a PhD in the Rock Engineering Group of Civil Engineering at the University of Toronto in 1992, under the supervision of the distinguished Dr. Evert Hoek, well known all over the world. Dr. Hutchinson engineering focus has been on integrating geological knowledge into geomechanics for underground and surface mining, mine closure planning, transportation corridor hazards assessment and risk management, as well as landslide monitoring and risk management using instruments and remote sensing techniques. Having enjoyed a marvelous career and incredible opportunities to work on challenging issues all over the world, Jean has been privileged to introduce thousands of students to the possibility of careers in these topics and to equip them with tools to engage with these challenges technically and societally. Recognizing the need to integrate and value the main perspectives on Earth Resources project, Dr. Hutchinson proposed and championed the Masters of Earth and Energy Resources professional program. She has benefited tremendously from the perspectives and insights of an increasing diverse group of students of several countries. Dr. Hutchinson is pleased to serve on the Technical Review Board of several organizations, including Rio Tinto's Bingham Canyon Mine and the Hong Kong Slope Stability Technical Board. Jean is an active member of IAG and of ISRM, contributing to their activity for many years. She has been IAG Vice President for North America in the last quadriennium, 2019 to 2023, and she is currently Chair of FEDI's JTC3 for Teaching and Training, and also a member of the International Advisory Board to the President of IAG. Professor Hutchinson has been recipient of a number of awards and medals, including the Glossop Medal in 2019, the IC John Sterling Medal in 2024, the Women in Mining Canada Trailblazer Award 2024, the IC Canadian Pacific Railway Medal in 2017, the Robert Schuster Medal 2016, and the inaugural Engineering Education Excellence Award at Queen's University, again in 2016. Jean has been elected as a Fellow of the Engineering Institute of Canada in 2011 and of Canadian Academy of Engineering in 2020. Volunteering for professional organizations is also a key focus for her. She is currently Vice President Technical for the Canadian Geotechnical Society, past President of the Canadian Foundation for Geotechnique, and member of both groups, the Women in Mine Stability and Women in Engineering Geology. Professor Hutchinson has supervised 30 MSc and PhD theses between 2007 and 2024. Along her career, she produced many publications, namely a book together with her husband in 1996, 7 book chapters, more than 60 articles in journals, and in the last 6 years, more than 30 keynote invited lectures offered in many countries around the world. Dear Jean, after this short presentation of the main aspects of your remarkable career, we are all waiting for having you up in the podium to present your lecture, which I'm sure will contribute to the prestige the Manuel Rocha lecture has all over the world.
Thank you very much for that extremely kind invitation, and to the Society here for the invitation to give this lecture. It's fantastic to see the family of Manuel Rocha here as well. Thank you for attending, and to all of you for attending this afternoon. I hope you can hear me in the back. It's okay? Yeah, perfect. Great. So I'm really pleased today to try and bring together engineering, geology, rock mechanics, and risk assessment. I wrote this abstract some time ago, and it's taken me quite a while to figure out how to bring those three topics into an hour and 15 minutes. So hopefully this makes sense to everybody. So as noted, I'm a professor emerita now, and that means that I continue to have some supervision of students in collaboration, but most of my attention now is turned more to the consulting side with innovative geomechanics. First, before I get started, most of the things I'm talking about today are the result of collaborations with many brilliant students over the years. You can see in the last 20 years here the 4 main projects that I've been involved in, and you can see the list of the names of all the students and collaborators, both from universities but also from industrial organizations. The biggest one is, you can see on the left side of the screen, is the Canadian Railway Research Program, which is now going into its 5th phase, so years 20 to 25, which is kind of unheard of in Canada in terms of collaboration between government, academic organizations, and the railway companies. And you'll see quite a few of the slides and concepts come from that project. Inspirations for this talk come from my research. So research on the left side, one of the main railway sites that I work on is shown on the left side. That's a 400-meter high slope. And in the summertime, there's probably 2,000 rock falls from that slope onto the railway tracks or onto the protection systems. On the bottom right are the Columbia River landslides. These are 3 kilometers in different dimensions, half a kilometer thick, massive landslides that have the potential to end up in the reservoirs of the Hydropower Corporation in British Columbia. The Åknes slide in Norway, I've just always paid attention to. I've visited it several times, and it's a very interesting case you'll hear a little bit about. And then more recently, on the review boards for both Hong Kong, for their slope stability program, and for Bingham Canyon Mine, which is the deepest copper mine in the world. So when I think about these rock slopes, you can see I've sort of rearranged this a little bit. And what you see on this slide are the same cases, but from left to right, with no human interaction on the left side through to full human interaction on the right side. So the left side, that is the Åknes slide in Norway, and that is a large natural slope which is anywhere from 700 to 900 meters above the water level in the fjord, with the potential to slide into the fjord and create a large tsunamic wave, a large wave. Next, we see the BC Hydro, or the ones in the hydro schemes in Western Canada, where those very large landslides have the potential to also slide into water reservoirs that have been created by the dams. The next one over is the railway sites, 400-meter high slopes with mostly rock falls, some rock slides. And that has, at the toe, about a 50 to 70-meter high rock cut. Those rock cuts were made in the 1800s, so there was no engineering of them, they were just cut. And so they now also create challenges from a stability perspective. And then the one on the right is the Bingham Canyon slope. This is a 1.2 kilometer deep open pit, and it's fully excavated from top to bottom. So those slopes are fully engineered from top to bottom. So from no engineering on the left to full engineering on the right. So when we talk about rock slope failure, there are different sort of categories of behavior. On the left side of this slide, you can see areas where there's collapse, and you'll see in these videos in a moment that these collapses occur very rapidly, and they may or may not have some run out from the location where they failed. And then on the right side, this is a slow-moving very large strain landslide in California. So I'll go first to the one on the left. This is from Korea, and this was induced after a substantial amount of rainfall. And you can see the rock slope failing. You can imagine that with no warning, the road below could, well, it certainly is inundated by all of this rock, and if there were cars or traffic below, they would be buried by this instability. This one, because of the geometry, mostly ended up on the road below and didn't really move very far beyond. The one in the middle is an instability from Bosnia, and on that image you can see blue arrows and red arrows. The blue arrows are highlighting locations where there are already tension cracks on the slope, and the red arrow identifies where they had a blast in the mine. And if you watch this, when I play it, you'll see the result of that blast. So the blast will be the very beginning. So if you look at the bottom, there's the blast in the quarry. Should be a normal blast, but it induced a massive rock slide. Not at all what they expected, of course. And the other thing you can see is that with that run out from that instability, it's creating a wave in the lake below. And so that's one of the big challenges with these instabilities. If they land in water, they will create these waves that can travel very large distances. So those are the two sort of ones we think of traditionally as rock slope failures, collapsing. But rock slope failures are also the ones on the right, where for more than 100 years, this large slope has been sliding towards the Pacific Ocean in California. And in the bottom picture, you can see a few years ago some work to try and reestablish the terrain, but the houses here just keep moving down slope. They keep adjusting the elevation of the houses, and they just keep moving down slope, moving down slope. So this, in my mind, is a failure, but it's being managed by different engineering activities. One of the ways we think about these kinds of instabilities is by the velocity. And so many of you, if you work in this field, will probably have seen this table or version of it, where one of the critical considerations is the class of the velocity. So you can see on this diagram or table from extremely slow at the bottom to extremely rapid at the top, and some ranges of millimeters per second velocity thresholds between those different boundaries. You can see also the human response to movement on the right side of this table, where in the extremely rapid, like we saw in those two videos, there's no real response that's possible. A person cannot run as fast as that upper velocity. In the middle, you have the chance for evacuation as long as warning is given and warning is heeded. People pay attention to that. The slowest ones, like the one on Portuguese Bend landslide I showed you, are the ones where maintenance is possible, and the assumption is that those will just keep moving and not turn into a catastrophic instability. So here's a cross-section through the geology of that landslide on the Pacific coast. You can see, in this case, the layers of shale here that are interbedded with volcanic ash. That volcanic ash converts to bentonite, which is an extremely plastic clay, and it's that surface upon which the landslide is moving. Again, this picture here shows you one of the intermediate scarps on this landslide as the movement is occurring downslope. When we look over here on the left side, we can see the range of velocities of this landslide, ranging from the upper end of the slough when it's very wet, when there's been rainfall, water infiltrating into the slope, it'll move at these higher velocities. And when it's a dry period, it still continues to move, but at these lower velocities. So this is a prime example of the type of rock slide that you can manage by maintenance of the buildings on the surface. Only recently have they decided on a prohibition of building in this area. Until a few years ago, people could build here as long as they had strong foundations on their houses. And the case in Bosnia I showed you, here's a couple of pictures of that instability in the quarry. And as you saw in those videos, those are extremely rapid instabilities that happened in the area where there's no response possible. So in that case, you really need to have warning in order to evacuate from those locations. And in the case of this quarry, because the blast was being held down here near the toe, there were no people in the quarry, so there was no influence on humans in that instance. But what you can see on this picture on the right are the two planes that basically created the sliding surface for that instability. You could see the cracks on the surface prior to the blast being created, but I think the assumption of the strength of the surface of these planes must have been that they were sufficiently strong to retain that large instability. So there was a very interesting lecture in 2010, which some of you may have attended. And this was a discussion about looking at geohazards and how to design with geohazards and considering the engineering geology of those. And one of the conclusions by that speaker and that author was that the damage that we're trying to design against depends on two main things. One, the speed, magnitude, and extent of the process, and the other being whether you can take action in order to control that process and to protect the elements that are exposed to its effects. So this was in 2010, and now we see many people drawing on these ideas where we really think about the upper point being the hazard that we're exposed to in terms of the context of risk, and the lower point being the consequence when you're thinking about the risk consideration. So what is the hazard? What is the consequence that really makes up the fundamental component of risk assessments? So this is a very old image from 2007 when Dr. Hook, Dr. Diedrichs, and I gave a course on risk management, but it's very simple, and that's why I continue to use it in this kind of context. So here across the top, you see the hazards, and down the left side, you see the consequences. So of course, when you have a very high hazard and a very high consequence, you have a very high risk, and you must do something about it. At the bottom end, you see a low hazard, low consequence, and in that kind of case, really you continue to observe, but there probably is not much you need to do about that at that time because it's both low categories. The sort of decision-making that's required in risk is in that middle part here, shown in yellow and orange, as to where you're comfortable accepting that level of risk. So the mining industry versus the civil engineering industry versus other industries like, say, nuclear power or nuclear waste have very different levels of acceptance of risk. And so this middle part really is, where is the acceptable risk? How does your industry consider that? But in general terms, this idea of hazard and consequence will inform the rest of this discussion today. So the first challenge when you're looking at issues of rock slope failures is that they're complex. Very often, the geological setting, the structures that lead to the instability are maybe only partially or unknown in many circumstances. The failure events are complex, and they can involve several stages of activity. The probability of failure, which we try and deal with in that risk context, and the time to failure is often highly uncertain. We really don't know when these things will happen. We can see evidence of potential for instability, but we don't really know when it will happen because there's so much variability in the materials that we're dealing with. So this is a video from the Canadian Railways. You can see that there was some rock already on the tracks. They stopped the trains, and then they were there to see that video or to take that video of the second failure. And then there were additionally third and fourth failures from this slope in the following hour or so. So these are complex. What part of it will fail and when will it fail? So when we think about the hazard, which we just saw, in general terms, we can try and keep water out of or remove water from the slope. We can support it with additional steel or concrete that we put on the slope to hold it in place, or we can try and remove it, or we can try and push material at the toe in what's called a buttress. So these are ways that you can mitigate those types of hazards. But the questions here are these possible? Are these technically feasible? How effective will they be? What will the consequence of failure be? And very often, this is driven as well by what kind of budget is available. Because there are so many unstable slopes, how much money is actually available to mitigate these situations. The next challenge is the range of consequences that might occur. So here again are 3 pictures from the railway project that I've been involved in for 20 years. The one on the left, top left, is a rock fall of about a cubic meter. And this is the sort of largest size rock that the freight trains in Canada can move aside. Anything bigger than this will likely lead to a derailment of those trains. And they're moving fast with a lot of weight behind them because they're freight trains. And so this is kind of the size of rock that we're mostly concerned about and above. On the top right, you can see a debris flow onto the tracks. That would certainly not be passable by the train. But in that case, generally they can clean up that debris and restore the tracks to passage very quickly because it doesn't damage the rails. The rock fall of that kind of size, if it lands on the rails, the railway tracks, it can lead to damage and lead to reduced capacity. And the picture on the bottom right is a rock slide that went across one of the railways in Canada, and that terrain derailed when it encountered it in the nighttime. And unfortunately, 2 engineers on the trains were killed in that instance when the engines went into the river. So we have a range of consequences in these situations depending on the size of the event. In addition, for the railways, there are 40,000 kilometers of track in Canada, but in this part of Canada, all of the freight traffic going west towards the ports in British Columbia are on a single railway line. There's one railway track in this area because of the varying sized valleys, and we have very few tunnels, unfortunately, in Canada so far. And so these are significant issues in terms of loss of capacity of the tracks, loss of revenue, and also user confidence. And as you see, you can have injury, life loss, or infrastructure damage in these cases. So when we're looking at reducing these types of consequences, we can look at a variety of things. If we put in a rockfall, high-energy rockfall barrier or a ditch, the objective is to hold that material on the slope even if it fails. That, of course, has a volume limit. There's only relatively small volume events that can be handled by that kind of preparation. Generally, avoiding is the best situation, so land use planning, relocating critical infrastructure, bridging or tunneling around these types of instabilities are key parts of avoiding. But if you can't avoid by any of those methods, then the next thing you can do is to warn and evacuate. And in that kind of case, again, we come back to that question of what is the rate and volume, when will that instability occur? So that brings us in warning and monitoring to this diagram. This is probably the central diagram for this talk because what we're trying to do is understand how these rock slopes will behave over time. So across the bottom is time, up the y-axis is displacement, and you can see a range of behaviors that we see in many materials, not only rock slopes. We see it in metals, we see it in soils, but we see these different curves or creep curves that give us an idea of how this material will behave. So the red line on the bottom is primary, where you have some displacement over time, but eventually the slope becomes stable. Very rarely in rock slopes, unless you take a lot of the water away, does this happen. More often, you're dealing with these types of situations where you have that startup of acceleration, displacement, you get into some sort of a steady state displacement, some number of centimeters or millimeters per day. And then in the cases I'll talk about in a moment, we then get into tertiary creep, where we see accelerating displacement with time. Sometimes that continues to be what's called progressive towards collapse, and sometimes it becomes regressive, and you sort of start over at the beginning of this curve again. So the big question in these rock slopes is how many of these cycles of progressive and regressive behavior can they actually tolerate before they fail? And you'll see as I go through this, there are different cases where slopes can move substantial numbers of meters, or they may move only small amounts before they collapse. And it's that distinguishment between the regressive and progressive behavior and how much disturbance has occurred on that slope that's really critical to this understanding and this management of the risk. So another publication from your group, this one from a lecture last year, you can see on this diagram a number of large landslides that Cassini collected together into this talk. And the way that you can look at this is, again, there's time and displacement on this curve, similar to the last one. And now that you've seen that previous curve, you can see many cases where there's progressive, regressive behavior happening in these slopes. And what he did was divide these into cases which led to failure, the collapse we've been looking at, occasional reactivations where you'll have some accelerating behavior and maybe something that becomes more stable, or ones that are very active and continue to move but don't collapse. And the scales on these are 10 meters on the y-axis on these two, and almost 7 years on the x-axis. You can see how long these cases carry on. And in the case down here of the active ones, that's a 5-meter scale and almost a 20-year scale. So you can see the differences in behavior and response of these slopes, which again, how do we interpret what is the progression and regression of these slopes? When will they potentially collapse? So this is a case that I'll talk more about in a few minutes. This is from Bingham Canyon. It occurred in 2021. This is what they call the Leo landslide, and I'll talk more about it. But in this case, this was well monitored with surface monitoring. And one of the big questions in a slope like this is a 500-meter high slope, and at the time that it failed, it had only deformed 1 meter. And then it catastrophically failed. So that's an extremely small amount of displacement before that failure occurred. So in this kind of case, what are the warning signs that you can look for? Are they detected? Can they even be detected? That small amount of displacement is very small for something like this kind of instability. And then when they're detected, how do you interpret the significance of those instabilities? We generally have incomplete information about the geological setting. We certainly have incomplete information about the sliding surface and what is the actual mechanism that will lead to the slide failure. And so the big question that I'm hoping to address here is, what is the capacity of the slope to deform before that failure occurs, before a catastrophic failure occurs? So in the case of open pit mining, when you're looking at managing those types of consequences, you can do, certainly this open pit monitoring and communication is a key part of managing any open pit. Managing these progressive, regressive phases of deformation. I'll talk more about it in a few minutes, but there's a way of managing the risk called a trigger action response plan, so a TARP. And these really depend significantly on what kind of thresholds you decide or you think are important to understand the behavior. And then establishing critical controls so that you keep people away from the areas of instability should they occur. So when we look again to these very natural slopes on the left through to fully engineered slopes on the right, we can see some different sort of general ideas. The first being that in the case of any engineered slope, a cut slope, whether it's at the toe of a large natural slope or whether you're creating a large open pit, you can learn from the previous excavations. If you're watching, you're monitoring, you're collecting the information, it gives you an opportunity to learn how that rock behaved, especially in open pit mining, because an open pit mine is mined a slope, and then they move back, mine another slope, mine another slope. Each time they mine a slope, you can learn from the previous one. In terms of the potential for instrumentation, it depends a lot on the potential consequence and therefore whether people spend money to monitor the slide. And the left three cases, generally we have limited knowledge of the rock mass and the slide properties. Even on the case of the Downey slide in the middle, that's a 3.5 kilometer by 2.5 kilometer instability, and there are 18 instrumentation locations across the surface of that slide, but that gives you 18 spot points of information. So we still have relatively limited knowledge of that slide and the slide properties. On the bottom, you can see the potential high consequences for worker safety because you have workers on the railway tracks, you have workers in the open pit mine, and then you have across the left three high consequences for public safety should these occur. Either because there are people in the way of the instability, or more often the left two waves that are created by those landslides causing influence much further afield than the rock slide itself. So a lot of people are turning to, have worked with the observational method defined by Dr. Peck in 1969, and it still stands the test of time in many ways. There's a lot of text on this slide, but what I wanted to do was just summarize here. The key concepts are that you're looking for the most probable conditions, recognizing that very often you have limited information about the engineering geology, the geological setting. You're trying to anticipate the most unfavorable but conceivable deviations, so not the wildest thing you might imagine, but things that are reasonably conceivable in terms of failure scenarios. Your design should be done considering the anticipated behavior, but you also need to think in design about a course of action for every foreseeable deviation. So anytime there's a deviation, you need to know in advance what you would do about it. Generally, if a deviation is occurring, you don't have very much time to respond to it. So if you haven't done that work to think about a course of action, you'll have a hard time responding rationally. Really, the focus of this talk is around the highlighted text, which is the measurement of the quantities that are observed, and therefore the evaluation of what you're truly finding as you're making that excavation. And then finally, if you see some deviation as you're doing that monitoring, you want to be able to modify the design considering those actual conditions that you have observed in that environment. He also said in 1969 that this should not be used, again, unless you have a plan of action. The observations must be reliable. They must reveal the significant phenomena, so what is the failure mechanism that is likely to happen? And they must be reported so that there can be a prompt response or action. So without the monitoring, the understanding of the phenomena, and the warning, you really don't have this observational method in a useful format. And then this idea of a progressive failure introduces a serious element of uncertainty. And so that's where we're really often dealing in these large rock slopes, is with quite uncertain and progressive instabilities. So back to this diagram again, when you get into those progressive failures, will they turn back to regressive? Will they become stable again? Or will they continue to collapse? And again, the variability of the materials, the size of these instabilities, it's extremely hard to have even a ballpark estimate of that in many circumstances. And this depends a lot on the potential consequence of failure. We're more tolerant of that uncertainty if the consequence of failure is lower. And can we mitigate that consequence? Do we have the money to mitigate that consequence? So the next part of the lecture, I wanted to talk about rock slope stability, engineering geology, and then risk assessment. And so in the rock slope stability part, I think anybody who's looked at rock slopes will have seen these diagrams. They've been around for quite a while, and they're very influential in terms of our understanding of rock slopes. So what we see here are ones where the structure either leads on the left to a planar failure, a wedge failure, or a toppling failure. And these videos show you that. So watch in the middle of this slide. You can see it's raining. A small block falls, and then the full planar instability occurs. So that's a sliding failure that occurred. One of my friends was the engineer for the highways in this circumstance, and she cleared out the news crew who took that video were standing right at the base of the slope when she first arrived, and within 5 minutes that instability occurred. So without her intervention, there would have been people in the way of that instability. The next one is the one you already saw, where there were two structures effectively creating a wedge failure in that case. And then the last one, in a moment, when the video finishes. Oh, we're getting the second one here. Yeah, so sorry that you can see that there's a second instability from up above, also on the sliding planes of a similar orientation. And the last one is a toppling failure. All of these are places where there was a cut made at a linear infrastructure site, leading to undercutting of these surfaces, leading to these instabilities. So this is a toppling failure in Thailand, adjacent to a highway, and you can see how the geometry permits that type of instability. So when we come to looking at monitoring programs, I'm not going to read this in detail. There's a lot of text here. This will be in the paper. But what we're seeing is that we need to assess the deformation. I've already been talking about that throughout this talk so far. We need to see those kind of discrete changes, like those fractures we saw on the slope in Bosnia. We need to understand the mechanism of the instability, what kind of structure is involved, how will it fail, what's conditioning that failure. Do we have water pressure within the slope? Do we have influence of blasting like we saw in the Bosnia case? Is there excavation that's undermining that slope, creating the instability? We generally, in this observational method, are trying to calibrate numerical simulations so we can try and understand those behaviors, understand what's influencing them. We use this data tremendously in the observational design method in terms of understanding the timing of these instabilities, and then we have input into the back analysis of failures. And as I said before, in the mining world, this gives rise to a method I'll show you later with a trigger action response plan that shows you how to respond to these observations that are being made. So when we're looking at large natural rock slopes, in most cases in my research, it's been with remote sensing tools like the LiDAR system you see here, and we're trying to understand the slope behavior, and then we're trying to detect evidence of instability, and then we're trying to interpret the deformation and failure mechanisms. So when we look at remote sensing technologies, there are many now that are available either terrestrial or via UAV or helicopter. And these give you different vantage points for looking at this information and give you different amounts of information depending on how close that monitoring system is to the slope. Here's some pictures of the tools that we've been using, and some of the advancements have been this ability to fly these systems on small UAVs and collect the data from a different vantage point, looking down at the slope. And then in the research work I've been doing with my students, processing this data automatically so that the information you need can be extracted very quickly from the data you've collected. Here we see an idea of the scale of the target. So when we're designing these systems, we need to think about how small or big the instability we're trying to detect is and what kind of warning signs you might see. This is an example from an open pit mine again, but you can see on the left side, relatively small instabilities, and on the right side, that's a 500-meter section of slope that's failed. So we're seeing very different levels of instability, and we need to design the monitoring systems to consider that. One of the tools we've used extensively is called a gigapan camera. It's basically an SLR camera, a camera with a large lens on it that is put on a robotic head. You can see that here in this image. And that robotic head rotates through a series of different positions, automatically taking photographs, which are then stitched together to make a panorama. There's no geometric information in this, but this lets you zoom in and with photos taken, in our case, 300 or 400 meters away from the slope, we can detect the difference between sand and silt and gravel on these slopes, because you can zoom into these images right into the position you're interested in. So they give you a subsequent, very detailed visual record. We've been working with a team from Sapienza with Dr. Mazzanti, and here they were using a surveillance camera, a relatively cheap surveillance camera. You can see the pictures in the middle. Those are taken every 6 hours of a section of the slope in White Canyon. And then tracking pixels using the photo monitoring software, we can see both rockfalls across the bottom, so the changes and rockfall locations. And on the right side, we can see movement within the debris channels as blocks are moving downslope in the debris channels. So this is a visual tracking using the pixels in those photographs. The next is a detailed record of the geometry itself. So this is done, in this case, with LiDAR, or in mining cases, very often with radar systems, you can see on the top left. But what you get from this is a data set where each gray dot on that picture on the right-hand side is a position in space, XYZ position in space, and in aggregate, it gives you the geometry of the slope. So in that model of White Canyon, the points are spaced at 7 centimeters on a 300 to 400 meter high slope. And when we look at that geometry from the LiDAR, we can see that 3D geometric data that we can get from, in this case, the terrestrial LiDAR data. We can see the rock sheds that they've built in White Canyon. You can see the debris channels coming over them. You can see locations where there are the cut slopes adjacent to the track, and you can see the full geometry of this situation. When we take this image and then one taken some period of time later, we can do a differential between the two images and we can see the change. So when I play this next video, anything in the sort of yellows and reds are locations where there has been material added to the slope, rocks falling onto the slope, and then anything in the blues and purples and pinks are locations where material has been removed from the slope. So there was a large instability that occurred here, and after that they removed material from the slope by the maintenance crews, and you can see the loss of that material shown in blue here. The natural processes basically occur from this elevation and up. So these are locations where rock falls are occurring and moving down these channels. And then these blue areas in this particular image are because of the maintenance work. So if you watch this, you can see the locations where change has occurred, and we can understand what's happening on this slope. And so you can see locations where they've been clearing the rock sheds. They were drilling and blasting some loose pieces in this zone and removing material again across these rock sheds. You can also see that a lot of this track is only protected by material falling into ditches, and so this information shows them when they need to do some maintenance work to give more capacity. The next kind of data category that we work with are situations where you can see contrasting properties. So this slide tries to show you something about thermal imaging of rock slopes. On the left side, these are data from Yosemite National Park in the US, where there are thin slabs of rock that exfoliate from these large intrusive bodies. And as those slabs of rock exfoliate, they gradually detach from the slope. It's not a single instant of failure. It takes time for that slab to detach. And you can see in this thermal imaging, the locations which are the most detached have the largest change in temperature as you get from sun to cold to sun, because they're detached from the rest of the rock mass. And the areas where they're not as much detached, where they're still attached to the rock slope, are shown in the cooler colors. So with this, you can see that progression of the development of that instability. The video on the right is one from the University of Arizona, where they've been working with thermal cameras to detect rockfalls. And what you can see here in an old open pit, they've pushed some rocks over. You can see here in this zone here, the color change. This is a change in temperature that's being detected, because as those blocks fall down, they're removing surface material, exposing material underneath that's of a different temperature. So that's not actually a black and white picture, it's the change in temperature that you're seeing. And so this is a new technology that has great promise and is being developed now and being used in sort of experimental situations in open pits. And then what you can get from all of this is something like you see here. This is one of the sites we monitor next to the railway tracks. These are larger instabilities that occurred over a 2-year period in this case. And what you can see are the shapes of those objects as they detached from the slope, because we have the information before the failure and after the failure. You can get an idea of what lithology they originated from. You can relate that to the rock mass structure and conditions. If we have sufficient data in time, if we have lots of data over a relatively short period of time, we can also get an idea of the velocity that leads to these instabilities. And this gives us an idea of the processes and the failure mechanisms that are occurring. So next, detecting evidence of instability. This is the large instability that I referenced a minute ago that occurred 2,600 cubic meters. It fell in the night with no warning in advance. There was no monitoring there except for the research data we were taking. My team actually stay in a rafting resort across the river from where this occurred. So they heard the rockfall, and then they got the LiDAR out and scanned all night as they were cleaning up the tracks. So what you can actually see is a shadow of an excavator here working to remove the material that fell on the tracks at night. The tracks in Canada are protected by these slide detector fences, which, when the wires are broken, they send a signal to stop the train. And so there was no injury or any other issue. And they had the track back to operations within about 8 hours after they cleaned this up. But the key thing for this situation is really the change again in the before and after geometry of this rock slope. So you can see the scale on the left-hand image here, plus 5 meters of gain to minus 5 meters of loss. And you can see that this instability was about 5 meters deep into the slope. When we did a back analysis on this, we could do a traditional kinematic analysis to look at what led to that failure. We can see a sliding plane here that led to that instability. We can see the approximate 5 meter thickness of this, and we can do a kinematic analysis, which if we had detected this backscarp, we would have known that instability was possible. But this is all back analysis in hindsight. When we looked back at our data sets, we could also see that prior to this instability, there were 2 other instabilities in the preceding 6 months adjacent to this And those become important when we look at this information. This is all the change in the preceding year, I think. Yeah, year of information. And what you can see here in hindsight, again, in back analysis, is that there were relatively small failures all around the lower edges of this larger instability. And there was also an undetected shear zone running parallel to the back of the instability, from which these previous failures occurred. So this is a case of understanding the geology and the setting after the failure occurred. But now that we know about this, we can, in this location, look for more of those shear zones. This section of track runs, as I said, all the freight for Western Canada, for both railway companies, and so you can never gain access to track. In 20 years, I've been on this track twice, in terms of actually having time to go there, because it's so busy, and so we have to do everything remotely, which is why these techniques become important. The final back analysis of this shows in the 6-week period beforehand, you can see this rock starting to topple towards the tracks. So towards the tracks is towards the screen here. You can see the amount of change in the normal vectors to relatively large amounts of displacement, but in this case still only about 0.15 meters of total displacement over that time before this one failed. But if you are looking at this data in foresight, you're looking for, again, this characteristic curve of acceleration up towards instability. And when you start to see that, you have a sense that there's something that might happen, even if you don't know what the magnitude of displacement should be at the time failure occurs. And we can see the top of this was moving towards the valley, and then the whole instability occurred on that lower sliding plane. So it gives us this idea of the mechanisms. So I have a few more examples here from these data sets. This is one where there are a series of debris channels that land either on a rock shed or protection shed or land in the ditches along this track. You can see here the result of one single storm event in November 2017, where almost the entire slope debris accumulation came off the slope and landed adjacent to the tracks or on the tracks. But what this gave us was the opportunity to understand where the back of those channels was. Before this, we'd only ever seen rock on that slope in those channels. But in this storm, because they emptied out entirely, we could establish actually what the baseline of those channels was, and then we could track, as the debris built up again, the volume that was building up on the slope. Until you get that kind of failure in these kind of circumstances, you don't really know where the back of this is. So how much is needed? The question was, how much debris needs to build up on the slope before one of these failures will happen again? The answer for this middle channel is shown here. There's about 158 cubic meters of material built up, and instability occurred. And then over time, we can see it building up, and then it failed again here. So we can get an idea of the volume that will build up on the slope before instability will occur again in a rainstorm. Here's another example. In this case, this is a flow basalt in British Columbia. And the challenge here is that rock falls coming from this slope can land on a dam of a reservoir. And so the concern here is, again, understanding what the thresholds are before instabilities will occur. You can see one that we observed. There's a 15-meter scale bar to give you an idea of how big that rock failure was. And when we looked at the data, we could see across these different locations this behavior of increasing displacement over time until failure. And we can see again that the top of this moved the most and the bottom moved the least. So again, this idea of a topple towards the valley before the instability occurred. This is a location, again, along the White Canyon, our research site, where we can see the 4 different lithological units that are exposed on this slope, ranging from intrusives to gneisses. And in all of these cases, we're seeing rockfalls. As I said before, about 2,000 rockfalls over the summer months in this location. And you can see plotted here on the left, the different volumes. So I said before, 1 cubic meter and below is really not of concern to the railway operators. It's these larger ones that are of concern, but these are ones that might give us an idea that another large instability is going to occur if we start to see them surrounding a moving block. When we look at this further, we can relate each of these blocks over here, or each of these locations, to the lithology, and then we can plot that over time. Again, this is a 15-month period, but we can see the magnitude of those, the frequency of those blocks versus the magnitude. You can see that depending on the lithology, we have different curves for this, which is an important consideration in risk. Which of these areas is most likely to generate the larger blocks, and how frequently will that happen? And this is what we need to know in terms of designing rock barriers or designing ditch capacity. And then the final example from this data set is one where we looked at a small section of track, because in this area, almost this entire slope over a 4-year period was fresh again. There were so many rock falls in this area that there was a fresh surface almost entirely exposed across this. Everything shown in blue occurred in our winter months, when we have multiple cycles of freezing and thawing and freezing and thawing. And the ones in red are shown in the summer months. But you can see how much more prevalent spatially the blue ones are, the winter ones. And when we looked at the data, you can see here precipitation over that period. You can see the temperature cycles over that period. And of key consideration is when they drop below this 0 degree line, because that is the situation that leads to frost jacking. In this first 2 to 3 years of the data set, we had about 7 freeze-thaw cycles per year and about 200 rockfalls during that time. But then in this latter period, we had many more, almost double the number of freeze-thaw cycles and almost double the number of rockfalls. So this is a very clear piece of evidence about those winter temperatures and those changes that are really important. And in this part of Canada, the thinking into the future with climate change is that freeze-thaw cycles will happen more regularly, that this will happen on a more regular basis in our wintertime, and therefore these kind of rockfalls will likely be a larger problem. When we also look at this database, we can see that we can pull information about the structural orientation of the blocks on the left side. So we can see the backscarps of the failures, and we can track the movement considering which of these surfaces it's sliding on. We can get an idea of failed blocks. We can map the structures onto the failed blocks. I'm not talking in this one about our work with game engines or physics engines, but we're simulating this type of instability using the same software they use to make movies, where they have bullets flying or cars crashing, same kind of thing for simulating rockfalls. And then on the right side, we can see surface roughness characteristics on the back here of that block that failed. So this is more information we can gather from this type of data, and information we never had before. So in all of this, can we provide timely warning? So we don't really know whether cycles are going to go progressive, regressive, how that's going to happen, but if it starts to move towards that, can we give warning? Can we collect, or are we collecting the data frequently enough to interpret that? And do we have sufficient confidence in our data and in the failure mechanism assumptions that we're making in order to establish what are reasonable thresholds? So this is the case of the Åknes slide in Norway. Again, about a 900-meter high potential rock slope instability into the fjords in Norway. There have been previous instabilities in this area, mostly along this channel here. There's a lot of instrumentation into the subsurface, as well as surface monitoring. that has given them the ability to both understand what the potential volume of failure is and also the sliding zones where the failure might occur. And they've developed models that you can see here, which look at the influences that would cause that instability to move more rapidly. So in this case, rainfall, potential for earthquake loading. And the bottom, this is a simulation of the size of the wave that would occur if that rock slide were to occur. So you can see on this scale bar, this is 50 meters of height of wave. Because if this rock slide occurs into the fjord, it's a very narrow environment. All the waves are focused into the fjord, and you can see run up at the ends of the fjords of approximately 50 meters. So they're simulating what the potential for this rock slide would be. There's a movie called The Wave, which is actually based on all of the scientific evidence collected from this. And this is a simulation of what that tsunami wave could look like in the fjord. This is a UNESCO World Heritage Site visited by many millions of visitors each year in these cruise ships. And this is the concern that if this were to occur, it would certainly influence the people who live in the fjords, but also would dramatically influence anybody who is visiting this location in a cruise ship. So the question here was, how do we interpret the monitoring data so that we have the ability to warn? Because in this case so far, there's no mitigation of that slope. There's only potential to give warning. They're considering drainage there, but it hasn't yet been implemented. So the people from the Geological Survey were charged with determining what the boundaries of deformation were that were required to give warnings. So we see across this diagram green through to red, depending on the velocities detected at the slope. So this comes back to the fact that the observations must be reported to give prompt action. And I'm not going to go into the details here, but basically there's an increasing level of warning. There's evacuation that's being done. Police are informed. The expert team interpreting the data are informed, and they become responsible for 24 hours a day as this progresses. And so with this, we can see a progression in both response, a progression in evacuation, and a progression in knowledge and communication. And we can see that up here at this red level of more than 10 millimeters a day, they're going to assume that this rock slide will come down. So they haven't met that yet, thankfully, but this is based on thinking about what are acceptable velocities. So now when we come to the engineering geology model that underpins all of this thinking, we need to develop these conceptual models of the geology. We have the main elements across the middle here, and this gives us an engineering geology model, the parameters for analysis, and some idea of the spatial distribution of the behavior. This is a recent publication from IAAG, very good document if you haven't seen it yet, on engineering geology model guideline development. And it's freely available from the IAAG webpage if you're interested. It's from Commission 25. And where the observational method comes in is really in this, again, this feedback loop that as you gain more information about the project, you can refine all of these models and continue to build your knowledge as you go. So when we look at these large rock slopes, here are some pictures from Doug Stead showing different instabilities like we saw, planar sliding, wedge sliding, and toppling. And then when we look at the assumptions about the geological setting behind these slopes, we can see two categories. The left-hand images are large rock slope instabilities on structures. In all those cases, those structures are pre-existing, and so there's sliding on those structures. And on the right-hand side, all those four cases require some internal deformation of the rock mass, fracturing in the rock mass, development of internal shearing, to permit these instabilities to occur. And so the hypothesis I'm still working on is that the ones on the left side give rise to that environment where you have the potential for that sliding to continue gradually over time, whereas on the right-hand side, once you reach a critical amount of strain and failure in that rock slope, you can have that more catastrophic instability. So this is from Bingham Canyon Mine. This is 2 slopes at that site. Although I'm on the review board there, all of this information is from published papers, so if you're interested, you can find all this in published papers. But the 2 slopes I want to talk to you about briefly here are this one here, called the O slide, and one here, which is the Leo instability I've already talked about. This is a porphyry ore body, copper ore body, and as you can see, the geological setting is quite complex. This O slide is mostly occurring in the intrusive materials, the stock material that intrudes up into the sedimentary sequences that you see here. And then the Leo slide is in a much more complicated geological setting that I'll come into in a moment. So first, the O slide. The O slide was mined in the late 1990s, 2010s to 2015s, 2016s, the first time around. And during the mining of this instability, they had substantial deformation that occurred, which they managed with this, I've mentioned before, trigger action response plan. So there's a trigger and there's a response that's enacted when you see these triggers. Again, these are all related to detected movements, millimeters per day of deformation or acceleration of the movement. So it's all related again to deformation, and they have categories of where things are routine and operational. Mostly this was managed by pausing mining. So when they saw one of those curves moving upward, they stopped the mining, let everything settle down, and then continued mining. And they did this progressive, regressive dance for the whole slope. They managed to mine the whole slope safely without a large instability of any sort. They did have information about if they saw larger displacements or potential for failure. They had different levels of removing people and equipment from the mine. They then recently started to mine a second pass into this wall. So they finished the first one, now they're mining the second slice into the wall. And during this instability, they saw large amounts of deformation during this mining. So here, this is the main haul road for the mine. This is where all the equipment goes up and down. There's no other location except for this. And this instability is right below this road. Each of these is about 30 meters high. Each of these benches is about 30 meters high. And what you can see at the bottom is over 4.5 months, this moved by 1.25 meters, especially in this zone over here. And you can see this all looks like progressive, little bit of regression, progressive, little bit of regression. And so what they're looking for is a little bit of regression before they start mining again. Then some of these larger events occurred after a series of rainfalls through the winter and spring months, leading to fairly large displacements, after which they stopped mining for a period and they let it go fully regressive. So again, it's this idea of balancing this deformation rate with the rate with which you mine. When they were mining this, they eventually mined over to a location that they didn't know held a shear zone. So they mined across to here, they exposed this shear zone, and when they exposed this shear zone, the whole thing really started to move. So this is another interaction that they hadn't anticipated. Again, they stopped mining and they were able to manage through it. But in this case, the engineering geology information was exposed by the data that they were monitoring. And this is a site where they have many drill holes, they have lots of information, but in a porphyry ore body, there are shear zones everywhere, and they don't know where they all are. And so this is a case where this material is just moving down between these two shear zones. This is a picture from the site visit we did 2 weeks ago. Here's this 10% ramp again, the main ramp for the slope. This is material that they've filled in to the ramp to keep the ramp running. So you can see how much this rock mass has moved down in this instability. Again, remembering this is about half, so this is about 600 meters of the 1.2 kilometer deep open pit, and you can see about 23 meters of fill into that area. They've also managed it by piling material here to hold back that instability and by removing material from the top. And they're managing this by, again, isolating the pit, pausing for let it slow down. And so they're managing this through and managing to mine through it, looking at that deformation rate. So the evidence up to this point was that they could have slopes that would go tens of meters of displacement without collapse. Then came the Leo failure. So this happened 4 months after I joined this review board, and this occurred May 31st. As you can see, this is 500 meters of slope height here, and this instability occurred, as you'll see in a moment, very rapidly. The final result was a failure exposing a very large shear zone and rock mass failures on this side of the instability with all of the material that failed out here. This actually ended up saving them money because this was mostly ore, and instead of having to blast the ore, it had mostly fractured in this case, so they were able to pick it up and move it away and actually save money, even though it doesn't look like that in this picture. So the geology, for those who are interested in the geology, there is this large through-going structure that they had seen before, but they hadn't realized either the extent of it or the very low frictional surface resistance on this. This is a combination of quartzites and carbonates that were intruded by this monzonite material. This is heavily mineralized, and this is the material that failed down. So what happened in this case, these pictures on the left are showing the amount of displacement of the surface of the slope on a month-by-month basis in the lead up to the failure, so the 4 months before the failure. And you can see sort of background amounts of displacement. These amounts of displacement, although they're covering most of the wall, were still considered to be background because the previous instability went for meters. In this case, you can see here that there was regression, progression, all the way through here until this period in January, February, when they took a blast at the toe. This blast, a very small blast at the toe, exposed some structure, and you can see that the amount of displacement really sped up, but it's still well within the parameters they thought before. This is only 15 inches, so about 15 inches, about a third of a meter of displacement at this point. So they weren't concerned because they'd seen tens of meters elsewhere on this slope. And then as time went on, they took a couple more blasts, and you can see here that this never recovered. This went to progressive, and there was no way to stop it. There was no way to stop mining because the removal from that structure had already occurred. And you see that the entire slope was deforming at that point as a result of these very small amounts of blasting at the toe. So in this case, they had velocity thresholds, they had pauses to try and allow the slope to relax, they isolated the toe from workers, etc. This is how they'd managed the other instabilities, but this one had such a small amount of displacement before the failure occurred that it couldn't be managed in the same way. So they inverted the velocity, and when you invert the velocity, it points towards a potential time for failure. They had the time for failure calculated within 23 minutes of when it occurred, which meant that they had both a surveillance camera across the pit and they had a UAV flying above the pit ready to collect the information from this. So in this case, this is considered a brittle failure. It happened very rapidly, and you'll see in the videos here, first, this one's a bit slow. It's sort of second by second from a surveillance camera. But you can see here as this goes where the main part of the instability is happening. Again, 500 meter high slope. You can see the failures happening here, then this part becomes involved, and then this part becomes involved. And if you watch down here, there's a downward motion which then turns into an outward motion. just there, now it's starting to have an outward motion. So this is showing you how this instability vacated that slope. This is the view from above. All of this is the blasting pattern. So these are the holes drilled down to make the next blast, which they didn't need to do. And you can see this vacating the surface. You can see all the rockfall dust down the side of the instability. And this is real time, so you can see how rapidly that instability is occurring on that slope. So again, a very small amount of apparent deformation before this failure occurred. So there was some back analysis done as well, mostly to try and understand where the high-grade ore ended up. So this is the pre-failure geometry, and each of these dots represents a part of the high-grade ore, so they could have a sense of where it ended up. This is actually a thermal camera. So it's an experimental thermal camera giving you information about this instability, tracking the blocks. The very white surface is showing up because that surface heated up substantially during that instability. You can see how much that was heating in the thermal camera on these slip surfaces, and you can see where these ended up. And then on the next image is some modeling using Itasca's PFC3D, showing you where these instabilities ended up. So this calibration of models, trying to give you this idea of how these behave. So the challenge that I think that we have now is to try and understand this capacity for deformation. Do we have small rock falls and or large volume rock slides where the sliding is understood, the frictional resistance to sliding is understood, and we have this sort of gradual movement towards a predictable instability? Or do we have what's on the right-hand side where we have this rock mass dilation, disaggregation, and in this case, this is something where you can have a relatively small apparent amount of deformation before it becomes irrecoverably progressive. So in the case of the sort of more understood mechanisms, what is the frictional resistance of the surface? What is affecting the strength? And can we forecast these conditions? Or are we in these situations where we're going to move into these tertiary responses without really having much warning? And in this case, these cycles of progressive regressive response, we really don't know what the cumulative deformation capacity is, especially in something like that Leo failure. And so as we gain more information from these databases, we get a better idea about how the rock mass damage accumulates and can lead to these large instabilities with relatively small amounts of deformation. So in the case of Leo, this is a picture from the toe of Leo just after it happened. We visited just after this happened. And you can see the debris at the toe. You can see this shear zone. And the interpretation now is that this rock mass rotated in a clockwise direction, sliding on this big surface, which allowed the rock mass on this side to dilate and become much weaker than it would be if it were just sliding normally. So this led to that increased aerial extent of deformation that we saw, and we could see the vectors of movement going from downslope to out of the slope, indicating this potential for instability. And this was, again, after a relatively small amount of instability. So to manage these, on the left side, this is our more traditional management of the risk, where we're looking at these deformations. We're understanding that we can maybe take some water out of the slope or put in material to hold it in place. And in this case, we're assuming meters of deformation, quite reasonably. The right-hand side, again, this idea of early detection, understanding the potential for that mechanism, and therefore, in this case, our mitigation may be very speculative. We may be doing things very early on when there's not much displacement because of the potential for this large instability. As we get into more extreme weather events into the future, we are going to run into these types of things more frequently, I think. Finally, in terms of the risk assessment, in most of these cases, I've been talking about the management of risk from a warning perspective in our natural slopes and from an engineer perspective in the constructed slopes. Because in the constructed slopes, we have a chance to respond to what we're seeing. In the natural slopes, we're responding to what nature's giving us. And so as we move forward in sort of realm of managing the hazard in large open pits, we see a number of things that can be done in terms of removing water or changing the geometry of the slope. This is the idea of the trigger action response plans. Again, this information will be in the paper, so I won't go through it in detail, but the idea here is that if you can't manage it by changing the geometry or removing water, you have to provide warning. And so again, you've got these different levels depending on your interpretation of the behavior and whether it will be like this slope, which becomes stable over time after significant displacement, or whether it will be a situation where it fails and collapses catastrophically. In risk acceptability, we also have to think about, will risk change over time? This is from an instability that occurred just before our visit to Hong Kong and the review board last year. This is a location where an old quarry had been used for the buildings you see here. And then during a very large monsoonal rainstorm, the water built up within the slope, leading to the instability that you see here. Large blocks came down the slope. They've been cleaned up here. In fact, one of the rocks bounced here and hit the window of a second story on that apartment, so big response in terms of energy. That's a change in risk over time. So when they first designed that quarry, it was fine, and then this is now 30, 35 years later, and you have this instability that's occurring. So we can't forget about the influence of time. So in terms of Dr. Peck's method, we can use engineering geology models. We can use these databases of events to give us an idea of potential failures. We have the calibrated numerical models you've seen a few of. We need to think about variation in the engineering geology model, in the pore pressure or water pressure in the slope. One of the key things is maintaining the monitoring. Even when it seems that it's a relatively small displacement, you need to maintain the information and interpret it. And then we can modify designs, but this is often designed on precedent experience because of the level of uncertainty in these materials. So the informed decision-making relates to thinking about the failure mechanism that we have. Are we going to have potential for this brittle or large deformation slope behavior? Key to this is development of these databases and repositories of event data so that we have a sense of what could happen in these environments, particularly related to deformation and the volume of the events. And then, as you may have seen in some of this integration and visualization of the data really helps us communicate the potential failure and support that informed decision-making. This has mostly been about surface data, not so much about subsurface data, but we cannot get a full picture of any of these slopes until we have some idea of the subsurface position of the instability. So that's a whole other lecture in terms of what's required in the subsurface. So I don't want you to walk away from this thinking that we can do everything with remote sensing, because we can't. We need to have some knowledge of that subsurface. And that in particular gives us some idea of the properties at depth and the influence of pore pressure on those shear surfaces at depth. So in terms of managing rock slope risk, we have to understand this potential slope response. Considering the geological model, we need to be able to forecast these types of failures and understand where there's potential for that brittle, rapid failure. Do we have an adequate balance of those subsurface instruments to understand the influence? And can we model that response well enough to forecast whether collapse will occur? And if it will, can we provide effective warning? So those are the final conclusions on this. I just wanted to say that one of the most enriching things in my career has been volunteering for different organizations. I know there's a lot of younger career people in the audience, and I would encourage you to volunteer for your local society or the IAG or ISRM or anything else that you can see in terms of giving back to the profession. The networks from this have brought me to know people like Ricardo and others, and it's just been a fantastic opportunity to work with other people around the world. So, obrigada for the time today and the opportunity. Thank you.
Boa tarde. Em primeiro lugar, gostaria de agradecer o honroso convite que a Comissão Científica da Lição me dirigiu para apresentar o voto de agradecimento à professora Jean Hutchinson, em nome de todos nós. Como certamente compreenderão, passarei agora a expressar-me em inglês. Madam President of the National Laboratory for Civil Engineering, Professor Laura Caldeira, Mr. President of the Portuguese Geotechnical Society, Professor Paulo Oliveira, Dear Professor Ricardo Oliveira, distinguished family members of Engineer Manuel Rocha, here represented by his daughter, Doutora Teresa Rocha, and his son, Engineer Manuel Rocha, together with their respective spouses, dear colleagues, students, and friends, esteemed lecturer of the 42nd Manuel Rocha Lecture, Professor Jean Hutchinson. It is a true honor to be here this afternoon presenting the vote of thanks on behalf of all of us and to have you all with us today. For more than 4 decades, the Manuel Rocha Lecture has been a defining moment in our professional and academic calendar in Portugal. Each edition affords us the privilege of learning from eminent voices in geotechnics, alternating between leading Portuguese and international experts, thus combining local perspectives with global insights. This year, Professor Hutchinson has enriched this tradition with her lecture on considering engineering geology in optimizing rock slope stability risk assessment. It has been a privilege to hear how engineering geology combined with risk-based approach provides a sustainable foundation for understanding, monitoring, and managing rock slope hazards in both natural and engineered slopes. We were privileged to hear compelling examples drawn from civil infrastructure projects, such as the Canadian Railway Research Project or the Hydropower Authority of British Columbia, where early warning systems play a critical role, as well as from surface mining operations, which remain a cornerstone of a country's economy and a sector of undeniable relevance to sustainable development worldwide. Mining not only drives economic growth, but also underpins the material foundation of the energy transition and the technology upon which our societies increasingly depend. Your case studies, Madam, demonstrated how geotechnical knowledge, when integrated with geological models, remote sensing techniques, and real-time monitoring data, can readily contribute to safer, more resilient, and more sustainable mining operations. Today's lecture reminds us that our work as engineers and geoscientists is not confined to theory. It protects communities, strengthens infrastructures, advances industry, and supports society in moving toward a more sustainable future. This edition of the lecture also carries symbolic significance, since Professor Hutchinson, you are only the second woman to deliver this prestigious lecture. Seated at the table of honor is the first, our distinguished Portuguese colleague, Professor Laura Caldeira, whom we also acknowledge with deep respect. Having both of you here today is deeply meaningful. It sends an inspiring message to the next generation that excellence and leadership in our field are not bound by gender. On behalf of the organizing committee and all present, I wish to express our heartfelt gratitude to Professor Jean Hutchinson. Thank you for your generosity in sharing your expertise, for showing the value of engineering, geology, and rock mechanics across infrastructure and mining sectors, and for reminding us how scientific rigor, when applied with vision and purpose, can truly make a difference. Thank you, Professor Jean Hutchinson, for sharing with us examples of the remarkable work in which you have led and inspired. And now I invite you all to join me in extending our warmest thanks and appreciation to Professor Hutchinson for her inspiring contribution to the 42nd Manuel Rocha Lecture. Please join me in a warm round of applause. Thank you.
Excelentíssima Senhora Presidente do Laboratório Nacional de Engenharia Civil, Professora Laura Caldeira, Excelentíssima Presidente da Associação de Geotécnicos Antigos Alunos da Universidade Nova de Lisboa, Professora Ana Paula Silva, Dr. Manuel Rocha e esposa, Doutora Teresa Rocha Félix e marido, que representam a família do engenheiro Manuel Rocha, uma referência para todos nós como cientista, engenheiro e cidadão. Dear Professor Jean Hutchinson, speaker of the excellent lecture we have just attended. Estimado Professor Ricardo Oliveira, caros geotécnicos, minhas senhoras e meus senhores. A 42ª Lição Manuel Rocha está a terminar. pelo que é a hora de começar a planear a próxima edição. Assim, é com muita satisfação que anuncio a 43ª Lição Manuel Rocha, que irá ocorrer em outubro de 2026. Para a próxima edição, a Comissão Científica escolheu para orador o ilustre professor Jorge Almeida e Sousa, que irá proferir a palestra intitulada Túneis em meio urbano. Considerando a qualidade do próximo orador da Lição Manuel Rocha, julgo que estão reunidos todos os ingredientes para que a próxima lição continue a honrar o nome do engenheiro Manuel Rocha e do próprio evento. Com periodicidade anual, tem vindo a ser realizado de forma ininterrupta desde 1984. Assim, convido todos os presentes a assistir à 43ª Lição Manuel Rocha, em outubro do próximo ano, e pelo que recomendo que reservem já esta data nas vossas agendas. Finalmente, gostaria de expressar os sinceros agradecimentos à Fundação Calouste Gulbenkian, que permitiu a realização de mais uma edição desta lição neste magnífico edifício. Quero aproveitar a oportunidade para, em nome da SPG, enaltecer o apoio da Fundação Calouste Gulbenkian ao longo de todas as edições da Lição Manuel Rocha. De facto, a generosidade da Fundação em disponibilizar as suas instalações tem sido fundamental para a realização de um dos eventos científicos mais marcantes da engenharia geotécnica nacional, tendo contribuído para a divulgação do conhecimento científico e técnico pelas mais relevantes personalidades nacionais e internacionais. I would all like to thank Professor Jan Hutchinson for accepting the challenge of delivering this lecture with outstanding commitment, competence and professionalism. Também gostaria de agradecer à Associação dos Geotécnicos Antigos Alunos da Universidade Nova de Lisboa e ao LNEC pela cooperação com a SPG na organização deste evento. À professora Ana Paula Silva e professor Ricardo Oliveira pelo cuidado que tiveram na preparação das alocuções que preferiram, e ao público presente, a quem desejo um bom regresso a casa. Finalmente, para as pessoas que vão participar na primeira gala, um até já. Ok, boa tarde. A presente Lição Manuel Rocha está fechada.